Okay, so let's start. Uh, in the last class, we were looking at the geodesic equation, and we arrived at the geodesic equation by starting with a free particle equation, which is written here, and this is a statement that the particle is undergoing no acceleration. And then we said that this equation, of course, would be invariant under Lorenz transformations. Uh, what we did was we looked at a general coordinate transformation, and we found that under a general coordinate transformation, which takes you from x alpha coordinate system to x prime alpha prime coordinate system, the equation did not remain form invariant. In fact, that equation gets modified into equation of this type. So notice that this second derivative piece is like an acceleration that is proportional to square of velocity in some sense. Okay, that is the kind of relation one ends up getting by doing a general coordinate transformation for a free particle equation in a particular frame. Okay, fine. Then what we did was the piece which was new had a coefficient, and we decided to call that coefficient gamma alpha beta gamma, and we just defined it this way. If you define it in that form, then you get an equation to take a form of this type. Okay, so this is just rewriting it, just replacing this additional piece that we got by doing general coordinate transformation. We just soaked it up by writing down the new notation. Okay, and we of course concluded that the free particle equation is not form invariant under general coordinate transformation. Okay, but the next thing that we wanted to do was that if we write down this equation, which we call equation 4, and if we do a general coordinate transformation here, would this equation be form invariant? Or let me put it a little differently, that under what condition would this equation be form invariant? And that would essentially determine how gamma would transform under general coordinate transformations. So what we are going to do, in fact what we did in the last lecture, was to demand that equation 4 remains form invariant under arbitrary general coordinate transformation, and using that we determine how gamma transforms. Okay, and that was the computation that we did. We just did an arbitrary transformation and we got some lengthy expression. That expression was kind of a repetition of what we did earlier, namely a second derivative piece throws up a term of this kind, and a gamma piece was just rewritten by replacing unprimed coordinate system by prime coordinate system. And then we said that if gamma transforms in this particular fashion, so imagine that the second term is not there. If the second term was not there, then gamma is actually transforming homogeneously. And when this homogeneous transformation is multiplied by these coordinate change pieces, you can see that that would make gamma behave like a tensor with one contravariant and two covariant indices. Okay, but that is not to be actually. In fact, gamma does not transform homogeneously. Gamma necessarily has a inhomogeneous piece of this kind. Okay, and and if you have an inhomogeneous piece of this kind, then of course gamma cannot be interpreted as a tensor. Okay, so the second piece is the one, the inhomogeneous piece is the one which is responsible for having non-tensorial property or transformation property for gamma. Okay, now of course if you do coordinate transformations which are at most linear, okay, like the, okay, I don't want to kind of roll back. I'll do the following thing. Okay, so remember, if you looked at a solution of this kind, okay, it tells you that, like, a free particle behaves this way. Okay, so similarly, if we had kind of tried to do a transformation, okay, which is x prime alpha prime is equal to some quantity times x alpha plus some other x naught alpha, which is like a linear transformation, okay, kind of Lorentz transformation or Poincare transformation. If you do that, then this inhomogeneous piece is not there. Okay, but that is precisely the class of interactions that we are sorry, the class of transformation that we are not interested in right now, simply because Lorentz transformations are the ones which of course preserves original free particle equation itself. Okay, what we want to do is to actually ask what happens at the general coordinate transformations which are outside the Lorentz transformation in some sense. Okay, and in that case this term is necessarily non-zero. Okay, fine. Now, so far we are, as I was saying last time, so far we had studied only tensors, and this is the first time we encounter a quantity which is not a tensor. Okay, and so this is one important non-tensor quantity that we would be using in general relativity. Okay, fine. The equation 4, which is the one which we will refer again and again, is called the geodesic equation. Okay, so geodesic equation basically tells you that if you are going from point A to point B, it is the shortest path connecting point A to point B. We will in fact see how it would be a shortest path soon. Okay, fine. Then I had given this as an exercise. I'm sure you must have noted it down last time itself, that one has to show that if you choose the original definition of gamma to be this, we need to show that it does transform the way gamma had transformed, the way we had written the transformation of gamma, such that the geodesic equation remains form invariant. Okay, so our original definition is consistent with the expected transformation property. Okay, fine. So let's try to look at another problem. Now, remember, when you are doing non-relativistic mechanics, classical mechanics, say, then there are two quantities, two kind of force problems that we study, which look pretty similar. One of them is, of course, Coulomb force, a charged particle experiencing a force due to Coulomb potential or electric field. And the other problem is gravitational potential. Okay, and that is of course a potential generated by some massive object and other test particle or smaller object experiencing the gravitational field generated by the massive object. At non-relativistic in the non-relativistic case, these two equations roughly look the same. Okay, so like suppose you had a charge with Z times E, which produces the electric potential or Coulomb potential, then Z times E times the elementary charge of the test particle, suppose we call that Q, then Z times E times Q upon R would be the potential, or would be upon R squared would be the force that the charged particle would experience. Okay, instead if you try to do this with gravity, then G times capital M would be the kind of part coming from the massive object, and G is the Newton's constant, times small m, which is the test particle in the experiencing the gravitational potential generated by mass capital M, would experience a force G times m times small m upon R squared. These equations seem to look pretty similar, and you would have thought that the gravity problem would have form which is similar to the form that electromagnetism has. Okay, so just to check whether that is the case, let us look at the Lorentz force equation in the electromagnetic theory. And so where we write down F is equal to E times the electric field plus E times the velocity of particle crossed with the magnetic field. Okay, we can of course write it in covariant form. I'm sure you must have studied this. F A alpha beta is del alpha A beta minus del beta A alpha, where A alpha is the zeroth component is the Coulomb potential, and A vector is the vector potential. Okay, the one which is responsible for, say, magnetic field. Now, F alpha beta, of course, by definition is antisymmetric in its indices. So F alpha beta is minus F beta alpha. And electric field is written as minus the gradient of the Coulomb potential minus the time derivative, partial time derivative of the vector potential. Okay, this I have just written just for notation purpose. Uh, Otherwise, I should have kind of written down a vector property here. Since everything is a vector here, I'm looking at F0 I as a component of a vector. Okay. Similarly here, B is a magnetic field which is a curl of A, and it is actually written as, if you look at ith component, then it is actually written as half of epsilon ijk fjk. That is the correct way of writing it. So this way of writing it is just to kind of indicate which component of F alpha beta are contributing to E versus the components contributing to B. This is, I shouldn't be calling it really equality. Okay, so let's kind of check what happens. So the first thing that you can check is a kind of simple exercise, is that F alpha beta transforms like a second rank tensor if A alpha transforms like a covariant vector. Okay, so this is of course a second rank covariant tensor F alpha beta. Okay, so of course you have to assume that A alpha transforms like a covariant vector. Okay, if you had made a different assumption that if A alpha itself has the inhomogeneous transformation property, then of course story would be different. Okay, but we know that the gauge field under coordinate transformation transforms as a covariant vector. Okay, so it's kind of a trivial exercise given the definition written up here. Sorry, here. Okay, fine. So using this covariant formulation, we can write down the components of the Lorenz force as F alpha is equal to E times capital F alpha beta V beta, where V is a velocity. Uh, Terrible notation. I should have used small v because I switched to small v next time. I'll correct that. Okay. So V beta, of course, has a zeroth component, and Vi is a spatial velocity component. Zeroth component is really kind of speed of light. Okay. Fine. Of course, F alpha is the rate of change of momentum. So you can kind of identify that with the Lorenz force. Okay. This expression is a covariant form of E plus V cross B kind of piece. Okay. Now, you can look at the zeroth component of that and the spatial component. It is this spatial component is the one which is the Lorenz force equation that we had looked at. Okay, so let me kind of write it down. Look at it again. Yeah. So this piece is actually Fi. F0 is a different quantity. Okay. Fine. Fine. So F0 is just a rate of change of energy of the particle, and we can kind of let it be. We want to kind of look at how this entire covariant equation behaves, but the interest for us is to look at the Lorenz force equation, okay, which is Fi. Okay, fine. So this, I mean, you can just check the dimensionality and you can figure out that this is basically work done on a charged particle kind of expression. Okay. Fine. So the equation of motion of a particle of mass m and charge E in the electric field would be written like this. Okay, that the force, which is m times the acceleration piece, written in terms of some parametric form instead of writing it in terms of d2x by dt squared. But nevertheless, you can always convert that into by trading of lambda to time. But nevertheless, this equation takes a form of this kind, where second derivative of x alpha is related to f alpha beta dx beta by d lambda. Okay, fine. So just to kind of bring it into the form that we had seen for the geodesic equation, we write down this equation in this form. Just pull the m down to write down this expression. Okay. Now notice that we had, I mean, in the exercise, we are already claiming that f alpha beta is a tensor. Okay. And we also know that dx beta by d lambda is a tensor. Okay. So therefore, this equation, okay, is in some sense a tensorial equation as against the geodesic equation, which is not a tensorial equation. Okay, so in that sense, the Lorentz force contains quantities which involve tensors, whereas the geodesic equation contains quantities which are non-tensors, okay, like gamma. So in other words, okay, so there's another piece which is kind of just sheer observation that the Lorentz force is linear in velocity, whereas geodesic equation is quadratic in velocity. Okay, so and because this Lorentz force is written in terms of tensors, and the tensors have the property that if they are non-vanishing in one coordinate system, then they are non-vanishing in all coordinate system because their transformation property is homogeneous. Okay, this homogeneity of the tensorial transformations ensures that if in one frame you see Lorentz force, okay, then it would be visible in every frame. Okay, no matter what you do with it. Okay, no matter what coordinate transformation you do. Okay. Fine. So in that sense, in the relativistic formulation, the behavior of gravity is different from the behavior of electromagnetism, in the sense that electromagnetism, the equations satisfied by electromagnetism are tensorial equations. If you see electromagnetic force in one frame, you will see that force in every frame, no matter what you do. Okay. On the other hand, gravitational force is not like that. Gravitational force is kind of a non-tensorial quantity, uh, and therefore there exists a frame in which you could actually nullify the effect of gravity. Okay, and in fact that is partly a statement of the equivalence principle, that in a sufficiently small uh, region of space-time, you can always choose a frame in which there is no force due to gravity. Okay, so this is something which you cannot do for electromagnetism, no matter how small the space-time that region of space-time that you want to look at. If there is an electromagnetic force, it will be visible always. Okay, fine. So what we have done really so far is only com computed, say, the geodesic equation by doing general coordinate transformation. Okay, and nevertheless, I have been talking about gravity and stuff like that, and I just made a statement about gravity. The force due to gravity is different from force due to electromagnetism when you set it up in the relativistic formulation. But in reality, we haven't actually shown that the force due to gravity has a behavior which is similar to what we had seen in the geodesic equation. Okay, so let us try to start again from the non-relativistic problem for gravity. Okay, and build it up and try to see in the relativistic form how does the equation look. Okay, fine. So here's the equation. The force that a particle would experience due to a gravitational potential is the gradient of the gravitational potential is generates the negative of the acceleration. Okay, and of course in the non-relativistic limit we have chosen the lambda to be kind of proportional to t, and that's why we have swapped lambda and t out here. Okay, but we can set it back in by putting this expression in terms of lambda and saying that if there is a linear relation between t and lambda, which is what you would do in the non-relativistic case, uh, this equation can be written as in this particular form. Okay, fine. So what we'll do is that we'll take this d lambda by dt on the other side and rewrite the equation. Okay, so that is the thing. Okay, fine. So once you bring this into a form of this type, okay, uh, this equation is an equation that we have written down for a non-relativistic particle. And of course, non-relativistic particle means we have done certain approximation or not approximation, certain assumptions about what are the velocities that are involved when one is trying to study a problem of this kind. Okay? And the assumption that we have made is that the spatial components of the velocity 4 vector in a relativistic formulation are much smaller compared to dt by d lambda piece. Okay, and that is the reason why only dt by d lambda appears here and dx by d lambda doesn't. Okay, Fine. So, so that is the kind of method of taking non-relativistic limit of a relativistic equation. Okay, but we can try to mimic, try to write down this equation into a relativistic form by appropriately elevating indices to relativistic indices. Okay, so instead of d2 xi by d lambda squared, we can set it to d2 x alpha by d lambda squared. Okay, now remember, x naught piece in the non-relativistic limit would vanish anyway, simply because the relation between t and lambda is supposed to be linear in the non-relativistic case. So this is a statement. So this piece, uh, we are adding nothing to the equation because this part is 0. Okay, but you could write down that remaining part of the equation as -1 over m times a alpha 0 0 dx 0 by d lambda whole squared. Okay, where a alpha 0 0 is just eta alpha j d phi del phi by del xj. Okay, so where we have assumed the gravitational potential to be kind of time independent. Okay, fine. So now you can kind of look at this equation, and it's quite reminiscent of the geodesic equation, because left hand side is a second derivative term and right hand side is some kind of a term which is quadratic in velocities. Okay. Now, since the spatial components of velocity are small, the spatial components are not appearing here, and only the temporal component is appearing. But nevertheless, the quantity is quadratic in velocity, which is what we had said was the difference between, say, the Lorenz force and the equation that you would have seen in as a geodesic equation. Okay, so therefore, if we covariantize this quantity and say that it is a alpha beta gamma, okay, then the a alpha beta gamma would kind of, you know, can be identified with gamma alpha beta gamma, and if you do that, then this equation basically reduces to the geodesic equation. Okay, fine. So what happens is that, like, the gravitational uh, potential actually generates a piece which in fact would have transformed inhomogeneously under general coordinate transformation, exactly the way gamma had transformed inhomogeneously. Okay, so as a result, what we see is that the effect due to gravity can also be mimicked by accelerating frame, because the geodesic equation was obtained by just studying a complicated accelerating frame. Okay, by accelerating frame, I do not mean that the frame with constant acceleration. By accelerating frame, I mean that the frame which does not have constant velocity. Okay, so it can have a non-constant acceleration also. Okay, so derivative of acceleration also could be a mm, kind of function of coordinates and so on. Okay, and that's what we would get if you do a general coordinate transformation. Okay, but nevertheless, what we obtained was that geodesic equation was obtained by doing a general coordinate transformation, and that would imply that you are going from one frame which you would have called inertial with respect to yourself to a new frame which is non-inertial with respect to you, and the equation had changed from a free particle equation to a geodesic equation. Okay, that geodesic equation has the same has the same form as what you would generate by studying, say, uh, a, a particle of mass small m in the presence of some gravitational potential. Okay, so as a result, we can kind of therefore claim that effect due to gravity can be mimicked by accelerating frame. Okay, and but in the accelerating frame, there is always exists a frame in which you can set gamma to 0. Okay, and uh, if you are in that frame, then you are essentially not seeing the effect due to gravity. Okay, so which is quite different from what would have happened, say, in the case of Lorentz force, where uh, no matter what frame you choose, you would always see the Lorentz force acting on the charged particle. Okay, Any questions here? Hello? Hello?
Yes, sir.
Yeah, okay. Any questions?
No, sir.
Okay. So let's continue. So we can now ask a question that suppose we start with the Minkowski space, which is the metric given here, or the line element given here, d tau square is equal to eta alpha beta dx alpha dx beta. Okay. We can ask a question, what is the effect of general coordinate transformation on the Minkowski space? Okay. So, of course, we have done a general coordinate transformation starting with the Minkowski space, but we only concentrated on the free particle equation. And we saw that under general coordinate transformation, the free particle equation became the geodesic equation. Okay. So that is something we know. Now we want to ask a question that that under the coordinate transformation of the same kind, what happens to the line element itself? Okay. So that is kind of easy to check. You go from x alpha to x prime alpha prime coordinate system, use a chain rule and replace dx alpha by del x alpha del x prime alpha gamma prime times dx prime gamma prime. Similarly, del x beta by del x prime delta prime times dx prime delta prime. Okay. So now if you look at this expression and the Minkowski metric expression, then you would say that the eta alpha beta times del x alpha by del x prime gamma prime times del x beta by del x prime delta prime, I can call this entire piece as some new metric. Okay. If I do that, then it has a form which is similar to this, except eta alpha beta is replaced by some new metric, whatever is this metric. Okay. What the form of this metric, of course, depends upon what is the kind of coordinate transformation that you are doing here. But nevertheless, tensorial structure is clear. Okay, it would be written as an object which carries gamma prime delta prime indices. Okay, so let's do that. We'll just define that to be g of gamma prime delta prime, which depends on coordinate x prime. Okay, and here is the form of the metric. Okay, so therefore, the straight line motion that we had seen in the Minkowski space would look like a geodesic motion in this metric. Okay, fine. But notice one thing, that we have not made any change in the space-time. Okay, it's the same space-time. In the same space-time, we have chosen same Minkowski metric to describe the space-time, or we could have chosen G gamma delta to be the metric to describe the same space-time. Okay, fine. So the straight line motion that we are looking at in the Minkowski space is actually a straight line motion even in the new coordinate system, even in the new metric. Okay, because a free particle is going to propagate in along a straight line. Okay, in the space, no matter what is the metric that you want to put. Okay, it is just that in terms of a new metric, the equation may appear complicated. Okay, and that is the reason why a simple free particle equation looks like a geodesic equation which has a connection piece gamma alpha beta gamma. Okay, fine. Okay, so one simple exercise that you could do is to do the following thing. You consider a free particle moving in x direction in Minkowski space, but now you replace Cartesian basis, which is x, y, z in spatial direction by r theta phi. Okay, and if you do that, then you can derive a free particle equation of motion under the coordinate change, which takes you from x, y, z coordinate system to r theta phi coordinate system. Okay, I have not given you the transformation here, but I'm sure all of you know what the transformation is. Okay, namely x is equal to r cos theta cos phi, and y is equal to r cos theta sin phi, and z is equal to sorry, the other way around. X is equal to r sin theta. Excuse me. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. Okay, excuse me. Uh, so, so use those transformations, and using that, you can check how the free particle equation would look like in r theta phi coordinate system. And in fact, you can derive gamma alpha beta in r theta phi coordinate system. Okay. Now remember one thing, that you can determine gamma alpha beta gamma even in xyz coordinate system. Okay. It's just that in xyz coordinate system, your metric is given by eta alpha beta dx alpha dx beta. Okay, and you need to determine gamma in that coordinate system. Okay, fine. So we will see how gamma itself can be written in terms of metric, which we have not done so far, but we will come to that in a moment. Okay. Okay. So we could ask a question that, do two different metrics give rise to two different geometries? Okay. So for example, here we already have two different coordinate systems, x, y, z, and r theta phi. Or if you go back, there is a coordinate system or the metric defined by eta alpha beta, and then there is a metric defined by g alpha beta. Okay, and they are related to each other by some complicated coordinate transformation. Okay, we want to ask a question that, if I give you a metric g alpha beta, and if I give you another metric g tilde alpha beta, okay, do these two metrics determine two different geometries? Okay, and we need to answer this question in a kind of most general form. Okay, and of course, tentative answer to this is not necessarily. Okay, uh, there are situations in which they would describe same geometry. For example, in this exercise, xyz coordinate system, you can attach time t to that, and r theta phi coordinate system with time t. Okay, that these two coordinate systems are just different choices of bases for the same flat space that we are looking at. Okay, so therefore, although the metric would take a different form in r theta phi coordinate system versus xyz coordinate system, they do not describe this. They do not describe different geometries. Okay, but the fact that this transformation did not generate different geometry does not mean that, therefore, if I write down some other coordinate system in another metric, it would not describe a different geometry. Okay, so therefore, tentative answer is that two different metrics need not necessarily describe different geometries. Okay, they could in certain cases, but they may not in certain cases. Okay, we will have to get a better criteria to distinguish metrics from whether they describe the same geometry or not. Okay, fine. So this is what I was trying to say, that if two metrics are related by general coordinate transformation, then of course they describe the same geometry, exactly the way x, y, z and r theta phi would be. The general coordinate transformation in this case is kind of trivial. We in fact know what they are. Both these coordinate systems are actually curvilinear coordinate systems. So in that sense, nothing very great is happening even in r theta phi coordinate system. But nevertheless, you can, given that there is a transformation which takes you from this coordinate system to this coordinate system, x, y, z to r theta phi, these two metrics would describe the same geometry. Okay. Now, given that you find something like this, you could ask a question that, can every metric be brought into a Minkowski form by general coordinate transformation? Okay. So we have already said that, like, that different metrics need not give you different geometries, but then you could kind of take the other extreme point of view and say that, like, okay, maybe there exists a GCT which relates all metrics to all other metrics, and therefore it is always possible to bring any metric to Minkowski form and you are done. Okay. And the answer to this is no. In fact, uh, it's not like all metrics can be brought into a Minkowski form. In fact, we can have a geometry which is non-Euclidean or non-Lorentzian geometry, since I'm talking about Minkowski form of the metric. Okay. And one needs to do a generalization of this geometry, and of course that was done more than 150 years ago by Riemann, and it's called the Riemannian geometry, which is what we would be using. Of course, since we are using space-time and not just purely spatial directions, which is what the Euclidean geometry would have described, we need to generalize the concept of Riemannian geometry, which would generalize Minkowski space to what is called a pseudo-Riemannian geometry. Okay. So is that okay? Any questions?
Yes, sir.
Yeah. Yes means there is a question or there is no question?
I don't have a question.
Oh, okay. Okay. Okay, so let's consider an example of Riemannian geometry. So what we are going to do is to consider a surface of a two-dimensional sphere, like a football, say. Okay, uh, there's a notation called to describe spheres. Okay, and the spheres are denoted by S, and the superscript on that tells you what is the dimensionality of the sphere. So circle would be written as S1, two-dimensional sphere will be written as S2, three-dimensional sphere will be written as S3, and so on. Okay, d-dimensional sphere will be SD. Okay, fine. So two-dimensional sphere is written in Cartesian coordinate system in this particular form: x squared plus y squared plus z squared is equal to a squared. Okay, that is the equation. Okay, now of course, given that you have an equation, implies that not all three coordinates are independent. Okay, so if you know x and y, then z is essentially determined because it has to satisfy this equation. Okay, and that is the reason why this space is actually called two-dimensional space, in spite of being described in terms of three coordinates x, y, and z. Okay, fine. So this equation itself tells you that not all three coordinates are independent. Okay, this is a kind of dependence equation. Okay, fine. So of course, here are the ways of writing this in other coordinate system. So uh, so instead of writing it in x, y, z coordinate system, we could have written it down in r theta phi coordinate system. Okay, if you write it in terms of r theta phi coordinate system, then there is one thing which is kind of immediately apparent from the kind of intuitive understanding of the sphere, is that if the center of the sphere is kept at the origin, then all the points on the sphere are equidistant from the center. Okay, that means the radius of the sphere is constant. Okay, you choose that to be any number. So we'll choose that to be r is equal to a. Okay, so if r is equal to a is fixed quantity, then any point on the sphere is only determined by what is the value of theta versus what is the value of phi. Okay, and r is not a parameter at all. Okay, and that tells you that the sphere is actually two-dimensional, because you really need two coordinates to specify any point on the sphere. For example, on the surface of the earth, if you want to kind of fix a particular point on the surface, all you need to do is to give the value of the latitude and the longitude of that point, and with the latitude and longitude you can pinpoint its position on the surface of the earth. Okay, now of course, if you are not uh, on the surface, but you are like elevated a few meters above the surface, then of course you'll have to give the uh, third coordinate. Okay, but if you are on the surface, which is precisely what is the definition of a sphere, that it's only that surface, then you really need only 2 coordinates. Okay. Now, of course, we will try to write down metric using Cartesian coordinates also, but polar coordinate metric is something we already know. This is something we have used earlier in, say, in quantum mechanics, in even probably in special relativity and so on. And the line element on the sphere is written as a squared times d theta squared plus a squared times sin squared theta d phi squared. Okay. So that tells you that g theta theta is a squared and g phi phi is a squared sin squared theta. Okay. Fine. And a is of course the radius of the sphere, which is a constant quantity, okay, constant radius object. Okay. But we could have chosen the original coordinates, which were like x, y, z coordinates, and we could have chosen, say, x and y to be independent coordinates. And in that case, z is a dependent coordinate and can be written as square root of a squared minus x squared minus y squared with some plus or minus sign. Okay, fine. So in the original Cartesian coordinate system, where this equation was written, x squared plus y squared plus z squared is equal to a squared, has the usual Euclidean metric or usual Euclidean line element written there, which is ds squared is equal to dx squared plus dy squared plus dz squared. Okay, but since we are studying the surface of the sphere, uh, z is not independent of x and y, and therefore dz squared is not independent of dx and dy. Okay, so what we will do is that we will look at z, which is given by this object. We'll use that to define dz squared in terms of dx and dy. Okay, fine. So here is the manipulation that we will do. Given that z is written in this particular form, you can figure out that dz can be written as minus x dx minus y dy upon square root of a squared minus x squared minus y squared. This is just ordinary differentiation, so no points for getting this right. All you have to do is take a dz here and just kind of replace that by taking appropriate differentials of x and y on this side. A is a constant. Okay, fine. So you substitute that up here, write down dz squared as square of this quantity and open it up. Okay, if you do that, then you get an expression which is like this: 1 over a squared minus x squared minus y squared. Quantity sits outside, and then you get everything written in terms of dx squared, dy squared, and dx dy. Okay, so it's for the first time we are seeing a metric in which you have something called an off diagonal piece. Okay, this is something we did not even see in the spherical polar coordinate system. Even polar coordinate system has d theta squared and d phi squared. There was no term like d theta d phi or say dr d theta or some such thing. Okay, but here we do. Okay, so what we get is a term which is like this: dx squared is multiplied by a squared minus y squared divided by a squared minus x squared minus y squared. Dy squared coefficient is a squared minus x squared upon a squared minus x squared minus y squared. And dx dy is independent of a in the numerator. It is just 2xy upon a squared minus x squared minus y squared. Okay. So that's how we read of the components. Okay. So first thing that we learn is that if you try to write down metrics on the subspaces determined by some algebraic equation, in this particular case, the algebraic equation was simple. It was just x squared plus y squared plus z squared is equal to a squared. But there is no reason why the algebraic equation would be as simple as this. You may have, like, say, x to the 6 plus y to the 4 plus z squared is equal to some number. That would look like some horribly complicated object, but it doesn't matter. You can ask, how would the effective metric on that surface look like? Okay, exactly the way we did it here. Okay, fine. Generically, therefore, what we would find is that the metric need not have only diagonal component. That is something that we are gotten used to in, say, special relativity, or even in the spherical polar coordinate system while describing, say, something like hydrogen atom or three-dimensional harmonic oscillator and stuff like that. But those are very special cases. Okay, generically your metric would have all kinds of components non-zero. Okay, notice another thing is that this expression is 2xy dx dy upon a squared minus x squared minus y squared, but I have written gxy to be just xy upon a squared minus x squared minus y squared. Okay, and the reason why we are not writing the factor of 2 is because the expression 2xy dx dy is actually gxy plus gyx. Okay, and gyx also has exactly same kind of form. Okay, well, that shouldn't come as a surprise because the metric G is supposed to be symmetric. So Gxy must be same as Gyx. But when you write that back in terms of the line element, then the line element, of course, would have off diagonal pieces appearing twice, once as Gxy and once as Gyx. Okay, so whatever is the coefficient that you get here, if you write down a particular metric coefficient, then that factor must be half of that. Okay, right? So the factor appearing here is not 2xy upon a squared minus x squared minus y squared, but just xy times that quantity. Okay, fine, good. So these are the coordinate transformations that I was kind of telling you some time ago, that under the coordinate transformations of this type, x is equal to a sin theta cos phi and y is equal to a sin theta sin phi. Okay, you can relate the xyz coordinate system to r theta phi coordinate system. Okay, so in fact you could write down z is equal to a cos theta also, in case you want to kind of utilize all the components of the coordinate systems in which the sphere is embedded. Okay, fine. So now, after having done this, you can kind of use this coordinate choice, and you can show that the metrics that we have obtained, namely in Cartesian coordinates, it looks like this. Okay, and in the polar coordinates, of course, it's kind of easy, like this. If you do a general coordinate transformation, these components of the metric would transform like components of second rank covariant tensor. Okay, so that is the exercise. Okay, that you check that if you do a transformation, say from xyz coordinate system to r theta phi, okay, subject to the condition that r is equal to a kept fixed, okay, you can show that that transformation would require specific factors like del x theta by del x, so del theta by del x and del theta by del y, and similarly for phi. Those kind of pieces would be required for you to go from g theta theta g phi phi metric to g xx g xy and g yy metrics. Okay, so please check that also. Okay, so I claim that this is an example of Riemannian geometry, and I also claim that the Riemannian geometry is different from the Euclidean geometry. And nevertheless, I said that, like, okay, you can write it down in terms of Cartesian coordinates, which describes the Euclidean geometry. Okay, so the question is, how do we know that this metric on a two-dimensional sphere cannot be brought into a Euclidean form by any coordinate transformation? Okay, and if we can answer this question, then we can kind of argue that S2 geometry is different from the geometry of any Euclidean space, I mean, in which, say, S2 is embedded, or any Euclidean space having the same dimension as the dimension of the sphere. Okay, in either case, we should be able to show that there is no way of going from S2 to that Euclidean space. Okay, So these two things are different because S2, if it is embedded, then S2 would be embedded in one higher dimensional Euclidean space, like XYZ is a three-dimensional Euclidean space, and S2 is embedded inside that. Or you could have a S2 related to the two-dimensional Euclidean space, and you could ask whether those two geometries are same. Okay, so in the first case, you go at least one higher dimension. In the second case, you are comparing geometries of the same dimension. Okay, and the answer is that in either of these cases, the metric on S2 cannot be brought into any of those forms. Okay, so let us ask the question: how do we develop a criteria which would allow us to distinguish different metrics? Okay. So what we need to do is to write down a quantity which is written in terms of metrics and its derivatives, okay, but it does not transform under a coordinate transformation. Okay, fine. Now, why do we want to write down these quantities in terms of metric and its derivatives? Any cases?
Because we know the transformation laws.
Yeah, that is one thing, but the reason why we want to do that is because it is the metric which determines the geometry of the space, which is described by the metric, right? So if you want to say that the geometry A is different from geometry B, then we look at a metric describing geometry A and a metric describing geometry B, and then we want to write down a quantity which is written in terms of metrics, and then use the metric, say GA, compute that quantity, use metric GB, compute that quantity, and then you ask, is this quantity same? If the quantity is same, then there is a good chance that these two geometries are same. Okay. If this quantity is not same, then you are sure that these two geometries are not same. Okay. So our criteria for determining whether the geometries are same or not are completely based on metric and its derivatives. Okay. That is the only available parameterization of geometry that we are going to use. Okay. Riemannian geometry is defined only in terms of the metric defined on the space. Okay. There exist other aspects of spaces, like what is called topology, which does not require notion of distance, and therefore no notion of metric is required. But if you are studying geometry, then you need to define a notion of distance, and that is the reason why metric would determine all the geometric quantities. Okay, fine. Okay, so now what we want to do is to show that this quantity, whatever quantity that we would be looking for, would say vanish for the Euclidean, flat Euclidean space, and it would not vanish for metric defined on S2. If that happens, then as I said just now, that then this quantity would be a litmus test to compare different geometries. Okay, now you could define only one quantity, you may find that two different geometries may have the same value for that quantity. Okay, but you could define yet another quantity and see whether they are same or not. Okay, so there are multiple ways of comparing quantities, but let's try to construct at least one. Okay, fine. Now we want the quantity to be invariant under coordinate transformations. Okay, the reason why we want it to be invariant under coordinate transformations is because you compare these two quantities corresponding to, say, geometry A described by metric GA. By GA I mean GA mu nu, and another geometry B described by the metric G B mu nu, and in one coordinate system you find them to be not equal. Okay, I mean, of course there are different geometries, so therefore a coordinate system used for geometry A and coordinate system used for geometry B have no reason to be same. Okay, but if you make a choice of specific kind and if they turn out to be different, then you could of course change the coordinate system, say for system B, and check whether the answer is same as what you got for GA. Okay, now if that is what is going to happen, then it's completely coordinate dependent quantity, and if you have a coordinate dependent quantity, then it is like the gamma that we have, that in some coordinate system it could vanish, in some other coordinate system it may not vanish. Okay, that is not an invariant description of any geometry. Invariant description of any geometry is it should not depend on any general coordinate transformation. You have to have a parameterization which says that this particular parameter takes value 1 here, 0 there, or value 1 here and 5 there. And if that is the case, then all the geometries are different. Okay, fine. Now we have been tom-tomming for some time that, like, all vectors, tensors do not transform. So one could wonder, why aren't we using just tensors? Okay. And the point is that, like, we really need to use components of these quantities, because although the tensor does not itself does not transform into coordinate transformation, tensor itself is written in terms of a specific basis vectors, like dx alpha is a specific choice of basis vectors. So what we want to do is to look at components of the tensor and construct a scalar quantity out of them, such that under coordinate transformation that scalar quantity wouldn't transform. Okay, and that is the reason why, in spite of saying that no vector, no tensor transforms under coordinate transformation, that is not good enough for selection criteria or distinguishing criteria between different class of metrics. Okay, so what we really want to construct is what is called a 0, 0 tensor. Okay, let's call it A of x, starting from g alpha beta and its derivatives. Okay, and as we just said some time ago, A is constructed from g alpha beta and its derivatives, because g alpha beta parameterizes the geometry of the space-time or space in general. Okay, it can be just Euclidean space also. Okay, so given that it is a 0, 0 tensor under the coordinate transformation, it will transform in this fashion. A of x is same as A prime of x prime. Okay, and therefore it is invariant. Okay, now suppose you choose two different metrics, say a GA mu nu and a GB mu nu, okay, corresponding to two different quote unquote geometries. And if you find this quantity A of x to take one value for one metric and another value for a different metric, okay, then there is no way you can find the coordinate transformation which would relate geometry A with geometry B. Okay, there is no coordinate transformation which relates G mu nu A to G mu nu B if this invariant takes different values for these two geometries. Okay, so this invariant therefore becomes a criteria for distinguishing certain class of geometries from certain other class of geometries. Okay, now of course, if A is same for G mu nu A and G mu nu B, still does not guarantee that those two geometries are same, because you can write down other invariant, okay, which may differ from one geometry to another geometry. Okay, fine. So any questions here?
What was the last statement that you said?
So what I said was that, like, you may have a geometry, say geometry A and a geometry B, okay, and it has some matrix written on that, and you may find that A of x constructed from both G mu nu A and G mu nu B are equal, okay, for some choice of A of x, okay. Now, if they are different, then you are guaranteed that the geometries are different. But if they are equal, you are still not guaranteed that the geometries are equal. Okay, because there are several invariants you can write down, and if one invariant is equal, does not mean that the other invariant is necessarily equal. Okay.
Yeah, okay.
Okay, so therefore, distinct values of A of x guarantees that the geometries are different, but same values of A of x does not guarantee that geometries are same. Okay. So it's in that sense a bit of a weaker statement, but it's also safer statement. Okay, it has a nice way of distinguishing things, but if they are same, you may need further analysis. Okay, so let's ask what kind of invariants we can write down. Okay, so the first invariant that we could write down involves no derivative of the metric. Okay, so which is like G alpha beta, G alpha beta. Okay, Now this quantity is just a number really, because you can just check that you can contract the indices and it becomes delta alpha alpha, which is just 4. Okay, since we are working in 4 space-time dimensions. Okay, so and this answer is 4 irrespective of what coordinate system you use, what matrix you use, it doesn't matter. Okay, so there is no way this object can distinguish different matrix. Okay, so therefore we can rule out this choice. Okay, then we could kind of ask, okay, what if I construct scalars uh, constructed out of G mu nu by not taking quadratic but more complicated functions, okay, but construct a scalar. Okay, and the problem is that, like, it would have the same problem. Okay, all such scalars constructed from only metric, okay, would lead you to some number and they won't be able to distinguish geometries. Okay, so therefore we need to construct objects which have the property that they do contain G alpha beta, but they also contain derivative of G alpha beta. Okay, and now after including derivatives of G alpha beta, we want to construct a quantity which is invariant under coordinate transformations. Okay, fine. So let's consider one derivative of G alpha beta. Okay, so if you look at one derivative of G alpha beta and try to do a coordinate transformation, so del alpha prime G beta prime gamma prime as a function of x prime, you can use a chain rule uh, to write down dx alpha by dx prime alpha prime times del by del x alpha acting on G beta prime gamma prime. But G beta prime gamma prime can be written in this form because it transforms like a tensor under this coordinate transformation. Okay, it's a second rank covariant tensor. So we use this fact that G beta prime gamma prime can be written in terms of G beta gamma in this particular form. Okay, so what we need to do is to take this partial derivative in, okay, and act on all the quantities that we encounter here. Okay, of which, of course, when del by del x alpha acts on G, that is pretty much like the left hand side, except instead of being in prime coordinates, we'll be in the unprimed coordinates. Okay, so that is the first piece, and that piece, of course, would have del x alpha by del x prime alpha prime, del x beta by del x prime beta prime, del x gamma by del x prime gamma prime sitting outside. Okay, so this piece almost behaves like a tensor. Okay, it's a homogeneous transformation. Uh, del of G is related to del of G times some transformation property. But in addition to that, you could have a term where this partial derivative doesn't act on G but acts on the terms beyond that. Okay, on del x beta and del x gamma pieces, and that gives you a new term. Okay, and this new term is not a function of del of G. It's a function of G, but not of del of G. Okay, so as far as partial derivative of G is concerned, this transformation is inhomogeneous. Okay, and the fact that it is inhomogeneous implies that partial derivative of G alpha beta does not transform like a tensor. Okay, so this is yet another place where we find a non-tensor quantity. So far, only non-tensor quantity we knew of was was gamma alpha beta gamma. Okay, now we have found one more quantity which also does not transform like a tensor, and that is the partial derivative of G beta gamma. Okay, so del alpha of G beta gamma does not transform like a tensor. Okay, fine. Now, given that del alpha of G beta gamma does not transform like a tensor, we cannot construct a tensor starting from a non-tensor. Okay, fine. So although G alpha beta itself is a tensor, G alpha beta and its one derivative are not good enough to construct a tensorial quantity, because inhomogeneous transformation piece involving partial derivative of G alpha beta cannot be cancelled off by writing down anything in terms of derivative of G alpha beta and G alpha beta itself. Okay, and therefore we cannot write down any invariant quantity. Okay, fine. Good. So in order to get a tensorial quantity, whose indices we could contract to go to a quantity which is scalar quantity and which does not transform, to get any such quantity, we therefore necessarily need to go beyond the first derivative of the metric. Okay, so we should necessarily have quantities which involve two derivatives of the metric. Okay, so to get that, let us define something else. Okay, and here's a definition. This object is called a Riemann-Christoffel connection. And just to quote Pauli, who always called it Riemann connection because Riemann had written down almost 15 years before Christoffel wrote it down. So he wouldn't want to kind of attribute it to Christoffel at all. But anyway, in general relativity, most of the time people refer to as Riemann-Christoffel connection. Okay. Okay, there is a small typo here. This bracket is closure of this bracket. I will correct that. Okay. Okay, so gamma alpha beta gamma is defined as half of G alpha delta times del beta of G gamma delta minus del gamma of G beta delta minus, oops, I think it's a bigger problem. Just give me a second. I need to correct that equation. Okay, I think I should get it right this time. Okay, so I hope you can see the corrected equation. So Riemann-Christoffel connection is defined in this particular fashion, which involves the first derivative of the metric and of course in inverse metric. Okay, so notice one thing, that I am using the same notation that I had used earlier, uh, which is gamma alpha beta gamma. Okay, and we had defined this quantity earlier in a different way, and we said that this transforms like a non-tensor. We have already found that first derivative of metric transforms like a non-tensor, and this is just a linear combination of first derivative of the metric. Okay, and what one needs to do is to check that if you do a coordinate transformation with and use this definition, you know how G transforms, that I mean G alpha beta would transform. Use that transformation property, namely G alpha beta transforms like a second rank covariant tensor, plug it in, okay, and take appropriate derivative. We have done this exercise earlier with various quantities. Even here we have done this. Okay, take this kind of pieces, plug it back in, and check that this new definition of gamma alpha beta gamma transforms exactly the same way that we had defined earlier. Okay, namely, it has a homogeneous piece which looks like a tensorial transformation, and then there is a, oops, there's one more error. and there is an inhomogeneous piece, which is the piece that we had used for defining gamma. Okay, fine, it will correct. Yeah, okay. So, so you can check that this definition of gamma alpha beta gamma has the same transformation property that our earlier definition of gamma alpha beta gamma has. Okay. Now the advantage of using this transformation, advantage of using this definition is that now the gamma alpha beta gamma, which is what we'll call Riemann principal connection, is defined completely in terms of the metric defined on the space. Okay. Earlier we are using everything in terms of general coordinate transformations, but general coordinate transformations generate geometries which are equivalent to each other. Because what we are trying to say is that if we have one geometry and if it is related to another, if you have one metric and if it is related to another metric by general coordinate transformation, then they do not describe different geometries. They describe the same geometries, just different choices of bases, different choices of coordinate systems. Okay, so we want to classify geometries such that classes of metrics are not related by any general coordinate transformation. And if that is the way we want to describe, it is better for us to write down gamma alpha beta gamma in terms of metric than in terms of general coordinate transformations. Okay, because this would allow us to do a distinction between different geometries. Okay, so this is a kind of simple exercise. Given that how the derivative acts on G has already been worked out, all you need to do is to plug it in and check. Okay, fine. So I think what I can do is I'll stop at this point and get questions. We can kind of continue looking at this going forward. Any questions? Hello?
Yeah,
Yeah. So if there are no questions, we can probably end the session here. We could start looking at other quantities starting from here. Okay.
yeah.
Okay, sir.
Okay. I just wanted to ask, just hold on.